Okay, good morning. Welcome to IvS seminar of today. Today we have Tinne, whom all of you know. Tinne has done her bachelor and her master at KU Leuven and is now completing her PhD, and we're going to hear about her PhD work today.
Yes, can you hear me? Yes. So thank you for the introduction, Rose. So today I will be talking about what I've been doing basically in the past 4-ish years in my PhD. So it's about high contrast imaging of massive stars, and more specifically, I am looking for and trying to characterize low mass companions down to the brown dwarf mass regime. So massive stars are born with at least 8 solar masses, and compared to sun-like stars, they are rare, and they live very short lives of the order of only a few million years. But nevertheless, they have a very important impact on their surroundings, so they emit ionizing radiation, which can have an effect on, for example, star and planet formation, and also through strong stellar winds and supernova explosions, they give heavy elements to their surroundings. So at the end of their life, massive stars might form a neutron star or a black hole, and these are gravitational wave progenitors. Now, if we want to understand these final end stages of the massive star's life, it's very important that we also understand the very beginning, so how these stars have been formed. Because any mistake that we make there can possibly propagate to the later evolutionary stages. So massive star formation at this moment is not very well understood, unlike low mass star formation. So just a very simple view of star formation in general. You start with a dark molecular cloud in which some overdensities like filaments and cores may form, and then parts of these filaments and cores can collapse to form a prestellar core, and this prestellar core can then start accreting from the cloud of gas and dust around it, and some of it can also flatten to form an accretion disk in which potentially planets or companions may form. Now, there are some reasons why we can't just see massive star formation as an upscaled version of low mass star formation with just higher accretion rates. Because massive stars, they emit very strong ionizing radiation, which can lead to photoevaporation of the surrounding cloud or of the disk, and thereby limiting the final stellar mass. Even this ionizing radiation can also have an effect on nearby stars, on their disks, for example. It can also lead to photoevaporation there. And it's a big question mark what this radiation can potentially do to companions that might be forming in a massive star's disk. So on the other hand, there's also a timescale problem. So massive stars have to form very, very fast. It's a very short timescale in which they form, so they have to accrete a lot of mass within that timescale. The accretion can still be going on even on the main sequence. And the disk around massive stars is also dissipated really fast. So for the formation of potentially planets or companions, there is not a lot of time. So a comprehensive theory of massive star formation is still lacking, and there are some reasons why it's very challenging to observe a forming massive star, because massive stars are located at large distances from us, so this limits the resolution with which we can look at them. They have a short formation timescale, as I already discussed, and they are during their entire formation deeply embedded in a cloud of gas and dust, making them optically invisible. So in this picture you can see a star-forming region where in the center there is thought to be a forming protostar, but it's very dark there, you cannot really see it. But if we know one thing about massive stars, is that they are formed in binaries and multiple systems. So we should rather look at massive star formation as a formation of a multiple system. So binaries are common, not only for massive stars, but also lower mass stars are found in binaries. So this plot is showing you the multiplicity fraction, so that means the fraction of binaries and multiple systems in a certain sample, as a function of primary mass. So you can see that the multiplicity fraction is going up, and by the time you reach the O and early B-type stars, almost all of them are found in these multiple systems. And moreover, for the O-type stars, about 70% will during their life even interact with a companion, which has a significant impact on their further life. For example, these stars may merge, or there may be some envelope stripping, etc. So it seems that multiplicity is already present at the very early stages of star formation. For example, this is the work from Emma Bordier, who did her PhD here last year. So it shows you, again, the multiplicity fraction, but now for different evolutionary stages in the massive star's life. So for embedded massive young stellar objects, so really the protostars, 0H main sequence O stars and main sequence OMB type stars. And what Emma found in her work is that for embedded massive young stellar objects, she found a multiplicity fraction of over 60%, which in that specific separation range of 600 to 10,000 AU agrees actually very well with the multiplicity fractions that are found at later evolutionary stages. So we can really see multiplicity as an observational constraint on massive star formation theories. So binary formation channels can mainly be divided into 4 different categories. So there is filament, core, and disk fragmentations. These 3 are all in situ formation mechanisms, so you form the companion at the same time as you form the massive star. And then finally, there's also dynamical formation through capture when you have stars that are passing nearby, for example. So all of these different formation mechanisms also represent different scales and evolutionary stages in the star formation process. For example, filament formation is really when you still have these bigger, long filaments in the cloud. Core fragmentation is when you have, for example, the prestellar core that may fragment, and disk fragmentation once you have formed a disk. So I will now go into a bit more detail about all of these mechanisms. Specifically, I will explain which kind of companions we expect to find for each of them, because each of these mechanisms can predict some different masses or different separation ranges for the companions that may be formed. So for core and filament fragmentation, you expect to find initially widely separated systems, but these companions may migrate inwards on a pretty short timescale of about 10 to the 5 years to form even spectroscopic companions. And since the stars in this mechanism collapse independently, but while there is still like a large reservoir of gas available, which they can both accrete from, it's very unlikely to have a system with a very massive star and then a very low mass companion. So you would expect a bit more equal masses in this case. So this has also been observed. So this is an ALMA observation of a high-mass protostellar cluster where they detected like multiple cores, and then within these cores they really found several fragments that formed many higher order multiple systems even. So they even found a quintuple system with 5 stars, and the mean projected separation that they found is about 730 AU. So that agrees very well with what we would indeed expect from core fragmentation. So for disk fragmentation, there is increasing evidence that indeed massive stars are formed with massive disks that can be very large, from a couple of hundreds to thousands of AU even. And these disks are very likely gravitationally unstable, and fragmentation in these disks can then lead to the formation of companions. Now, fragments don't necessarily have to form companions. They may also merge with a central star, for example, or they may be destroyed, and maybe some of them are ejected out of the system. So a lot can happen to them still before they necessarily form a companion. And then the companion mass in this case will be dependent on the disk dispersal timescale, because it is thought that companions can also accrete from the disk in this way and then also become very massive. But of course, massive stars also disperse their disk quite fast. So in this case, you could also expect to have more lower mass companions, for example. So there are some simulations for disk fragmentation, specifically around massive stars, and these predict that the fragment mass is usually of the order of about a solar mass. But then the fragments may, of course, still accrete from the disk. I think they also found a companion in their simulation that was in the end about 6 solar masses. But a strong limitation of these kinds of simulations is the computation time, the computational cost, because I think they did this simulation up to a few 10,000 years, and it would be very interesting to also know what happens later to the fragments, because they might be destroyed or merge with the central star, or they might accrete. There's a lot of things that we don't understand yet very well. There's also this very interesting observation of disk fragmentation. So this is again an ALMA observation, and in this case they detected a very low mass fragment of below 0.6 solar masses in the disk around a 4D solar mass proto-O star. And the separation, as you can see, is about 1,900 AU. So in this case, the disk indeed is also very large. But again, we are unsure about the fate of the fragment. It's a very early stage still, so it might still accrete. It's not sure yet that this fragment in the end will really form a companion around this massive star. And then the final mechanism, capture, so formation of binaries through dynamical interactions. This is likely less common than the other ones. For example, recent simulations of binary populations have shown that only less than 5% of their binaries were actually formed in this way. But of course, it also depends strongly on the density of the cluster. So this mechanism is thought to produce widely separated systems. And in dense environments, you can expect more interactions, which can lead, of course, to more captures. But interactions can also lead to disruptions of binaries, and it seems that this disruption wins. So the wide binary fractions in very dense environments are usually lower. So then there is still a big question that we have, because current observations mostly of massive stars in binaries mostly cover mass ratios that are larger than 0.1. And this is, of course, because of instrumental limits, so it's very challenging to find a low-mass companion around a very massive star. But one thing that we don't know is if these low-mass companions actually exist, because massive stars emit this very strong UV radiation, so this creates a very harsh environment to think that such companions could potentially form. For example, as I already told you in the beginning, massive stars with their UV radiation can even photoevaporate the disks of other stars in the neighborhood that are not even forming as companions around them. So we're very unsure about the effect on companions that are even closer to the massive star. So what we need to get a better understanding of which mechanisms are at play, which mechanisms may be the dominant ones maybe, and we need observational constraints. So in order to probe the full range, the full separation range of companions around massive stars, we need to combine different observational techniques. For example, for closer companions, you can use spectroscopy. For intermediate separation companions, interferometry is very important. And then as you go to the wider separations, you can use high-contrast imaging. And it's also thought that in each of these separations, maybe one mechanism may be dominant over the others to form companions. So as you can see also at the top. So concretely, what we want to do is we want to observe the companion mass ratio and separation distribution around massive stars in different environments. So we also want to see the effect of age, for example, how these multiplicity fractions change as the cluster evolves. We want to probe different densities to see what effect the density has on these multiplicity properties. So one such study that combines different observational techniques is the SMASH survey. So they used interferometry and imaging to find mostly bright companions around massive O-type stars. So I show here a plot also, and how you should read it is on the y-axis is a contrast magnitude of companions with respect to their central star. So that means it's the brightness difference of companions compared to the central star, and then on the x-axis is the angular separation of each companion with respect to its own central star. And then the full lines that you can see in this plot represent the contrast curve, so that's the sensitivity limits you cannot observe below the contrast curve with a certain instrument. Now, the reason that I showed this study is because I want to compare it with the CHIP survey, and that is a Carina High-contrast Imaging Project of massive stars. So in this survey, they used VLT Sphere, which is a high-contrast imaging instrument on the VLT, to probe the multiplicity properties of massive stars at mostly wide separation ranges. But as you can see, the contrast curve suddenly goes down a lot, so we can probe a completely new parameter space with high contrast imaging compared to these techniques that we previously had. So this is also very important to solve the question of whether low mass companions can exist around massive stars. So SPHERE stands for Spectropolarimetric High Contrast Exoplanet Research. So as the name suggests, it's mostly used to find exoplanets around solar-like stars, but in a scaled-up version, we can thus also use it to find low-mass companions, possibly even substellar companions around massive stars. So what does sphere data look like? Well, in the center we put a coronagraph that blocks the light from the central star, and this significantly increases the contrast that we can reach. And then the data is organized in a 4-dimensional cube. So on the one hand, we have the 2-dimensional image, where we use 2 different science instruments called IvS and IRDIS. And IvS gives us a smaller field of view of up to 0.9 arcseconds, while with IRDIS we can probe separations up to 6 arcseconds. Then a 3rd dimension consists of different wavelengths. So for the IvS instrument, we get 39 different wavelengths, and that's very interesting because it means that if we detect a companion that is within the IvS field of view, we can extract a low resolution spectrum for it and characterize it. And then for IRDIS, we only get 2 wavelength bands. And then the final dimension consists of different rotations. Now, what are these rotations? Well, so normally, when you would observe, the sky is rotating with respect to your telescope, and you would also rotate the telescope with the sky so that your image is always oriented in the same way. With high-contrast imaging, we don't do that. So we just keep the telescope rotation fixed, we don't rotate, and we let the sky rotate with respect to the telescope. And the reason that we do this is because there is, even though we use a coronagraph, still a lot of noise present in the images, a lot of speckles that we can potentially also confuse with the true sources that we want to detect. But by letting the sky rotate, we actually make sure that any true sources will also appear to rotate in the image with respect to the central cell, while the noise will stay constant. And this creates a differential behavior between the noise and the true sources. So then by combining these images in a special way called angular differential imaging, we can actually reduce the noise and thereby also enhance the signal of our true sources. We also do something similar called spectral differential imaging, and that is based on the fact that we have multiple wavelengths and the fact that the PSF of the noise will get larger with wavelengths. So by now we have accumulated many VLT sphere samples for which we have observations. And one of them is Sco OB1, which is an older region from 6 to 8 million years, and we have 19 stars in this sample. Then we also have a sample of 39 stars in the Carina region, which is younger, so this is a CHIPS project that I talked about earlier. Then we have 10 O-type stars in M17, which is an even younger region. So this allows us to compare how the multiplicity fractions change as a function of age. Then we also have 7 stars in Trumpler 14, which is about the same age as M17, but it's much denser. So in this way, we can also compare what effect the cluster density has. And then finally, we have a sample of 15 stars in the field and in loose associations, which we can again compare with our cluster environments to see if density has an effect. So I will focus now on the observations of Sco OB1 because that is what I mainly did during my PhD. So the Sco OB1 association, it's an active star-forming region of which you can see a picture on the right. It's 6 to 8 million years old, and it's at a distance of about 1.5 kiloparsec from us. So for sphere, this means that we are probing physical separation ranges of about 225 up to 9,000 AU, so really the wider companions. And we have a sample of 19 OB stars, from which 13 are O-type and 6 are B-type stars. So for the data analysis, we start with the cube that I showed you earlier, where in the center we have the coronagraph, so we have multiple images, but we combine them by doing angular differential imaging, and then we get a post-processed image that looks like this, where we suddenly can see a lot of sources. So this is the IRDIS field of view. And then if we compare that with the IvS field of view, which is a lot smaller, you can see that in this case we detected a companion there, or a source at least. And that's very interesting because that means that we can characterize it by extracting a low resolution spectrum and comparing that with atmosphere models and evolutionary tracks. So in this case, we found a mass between 0.1 and 0.25 solar masses at a separation of about 540 AU. So really a very low mass companion. Now going back to the first image, you can see that we found a lot of sources, but it's important to realize that not all of them are bound companions to the central star. In fact, most of these are there due to background contamination. And it's very important that we find some methods to distinguish these background contaminants from our true companions. And you can either do that by taking a follow-up observation, so you wait a few years, and then you can test for common proper motion of the sources with the central star. Because if a companion is bound to the central star, you expect it in any case to move together with the central star, while your background may be static or move in a different way. However, that takes a long time because you have to wait a little bit also before your stars have moved enough to do something like this. So what we do instead is that we rely on some statistical properties to say if a certain source is likely a bound companion or not. So we call this the spurious association probability. So what is this? This is a probability that a certain source is a background or a foreground object. So basically the probability that you can explain your source as being a background contaminant. So how do we calculate this? Well, imagine that here we have a source that we detected in the sphere field of view. What we need from information is we need to know what the expected background contaminants look like. So here I selected specifically only the background sources that are at least as bright as this source. So that are the only ones that we can really be confused by. So what we do then is that we see, well, what is the probability of finding at least one background source within the separation where we've detected our source. And this gives us the spurious association probability. So this gives then a summary of all of the sources that we detected in Sco OB1. So it's again a similar plot as I've shown before, where on the y-axis you can see the brightness of all of the sources, and on the x-axis the angular separation of each source with respect to their own central star. And the different colors in this plot, they are the spurious association probabilities. So you can really see that, for example, the closer and brighter sources, they have a low spurious association probability, meaning they have a very high probability of being bound companions, while when you go to fainter magnitudes, you find that lots of these sources are very likely background contaminants. So on this plot, we can also show the region where we would expect to find brown dwarfs and exoplanets, just based on the absolute K-band magnitude. And then you can see that we are really probing the brown dwarf mass regime around massive stars. However, not yet the exoplanet mass regime. But most of the sources that are located in this brown dwarf region actually have a very high spurious association probability. So therefore, it would be really nice if we could take some follow-up observations and actually measure their proper motion. So for the multiplicity statistics in the sample, so we found a total multiplicity fraction of 89%. This is also including already previously discovered companions. And then I can also show you the companion fraction, which is the average number of companions per star. So I divided it into O-type and B-type stars in the sample of Sco OB1. And for only high-contrast imaging, we actually found a much higher companion fraction for the B-type stars than for the O-type stars. But this is not what we expected, because if you remember the plot from the beginning, multiplicity goes up with spectral type. So we thought, oh, maybe we are missing some closer companions, like O-type stars might have more close companions than B-type stars. And that is indeed the case, but still the companion fractions are 3.3 for O-type stars and 4.4 for B-type stars. Of course, the sample is very small, so we had only 6 B-type stars. It's not a lot, so it could be because of that. It could also be because of different sensitivity limits. So the B-type stars are less bright. Maybe we can probe fainter companions around these than we can around O-type stars. Of course, it could also be a real effect, because this like low mass companion regime hasn't really been studied a lot. So it could be that for some reason there are more low mass companions around B-type stars than O-type stars. But what we would need to do to solve this question is either increase the sample or also perform some bias correction to see what the effect is of the different sensitivity limits, for example. So then we can compare our companion fractions that we found as a function of age, so using these different samples where we had sphere data for. So For this specific comparison, I am only including the IvS companions because they are so close to the central star that they, in any case, have a very high probability of being true bound companions. So it's harder to explain them as background contaminants. And it's also important to know that this is not yet bias corrected. So all of these regions are also at slightly different distances from us, which means that we are probing slightly different separation ranges. So that is definitely something to take into account in the future. So for Scorpius OB1, we found a companion fraction of about 0.26. And then for the Carina region, which is younger, we found a similar companion fraction of 0.39. And then if we look at the even younger region, M17, we actually found a companion fraction of 0.6. So that is much higher than what was found for these older regions. And interestingly, also a lack of spectroscopic binaries was previously found in M17. So this youngest region seems to have more wide companions, but less close companions. And this could possibly point to an effect, an evolutionary effect, where these binaries are formed further out, and then later on, if the cluster gets older, migrate inwards. Of course, the sample of M17 was also only 10 stars, so it's still quite small, and we would have to do the bias correction to be sure about this, but it's a first result. So then we can also compare it as a function of cluster density. So actually, if we compare the Carina region with Scorpius OB1 and stars in the field, we find very similar companion fractions. But if we start looking at M17 and Trumpler 14, where Trumpler 14 has a much higher density, then we actually see a difference in the companion fractions. So we see that in the very high density region, the companion fraction, the wide companion fraction is a lot lower, which could actually be expected because in this case, there are more dynamical interactions which lead to more disruptions of the binaries. So then something else I want to show are the low-mass candidate companions that we detected specifically in Scorpius OB1 and in the M17 region. And I want to point out the ones on the left. So I show the mass, the estimated mass of the companions in the top of the plot every time, and then in the bottom is a spurious association probability that we calculated for them. But the ones on the left, these are candidate companions that are in a brown dwarf mass regime. So we even have one B-type supergiant, the one on top, where we found 2 brown dwarf candidate companions that are really close by. So it would be very interesting to, at some point, obtain follow-up observations of these. For now, we did get follow-up observations for 3 other stars. So all massive stars with a low mass, so below 0.3 solar mass companion. So these follow-up observations allow us to test for common proper motion. Now, if we want to distinguish true companions and background sources by checking the proper motion, a crucial requirement for this to work is that the proper motion of your central star is significantly different from the background. So in this diagram, sorry, spoiler, I show you the proper motion in right ascension and declination direction of background sources. And this I got from the Besançon model of the galaxy. It's a model where you can simulate the stellar contents and kinematics in the Milky Way, so specifically in the line of sight to Scorpius OB1. And the lines are contour lines. So on this plot, we can put the proper motion of our central stars, or one of them is Scorpius OB1, and you immediately see a problem. Some of the background sources are co-moving with the central star. So that is sad, but okay, we move on and we calculate the proper motion of our low-mass candidate companion. So in this case, these are 2 measurements, so one from the IRDIS instrument and one from IvS. So it seems to be relatively close to that of the central star, especially if you take into account the error bars. And to be sure, we can also plot the proper motion of sources in the wider IRDIS field. Okay, they have large error bars, but you can see they seem to move in a different direction compared to the low-mass candidate companion, which stays with the central star. So because, of course, the background is still co-moving, well, at least some of them, we cannot be 100% sure that this companion is actually a true bound companion. So we still rely on probabilities, but there's an advantage because we can calculate a new spurious association probability, where in this case, instead of taking into account as potential background sources that can confuse us this whole diagram, we can focus specifically on the background sources that are co-moving also with the central star. And this significantly reduces the spurious association probability. So we are at least more certain that they are in fact bound. So by doing this analysis, out of the 3 targets for which we had follow-up data, we identified 2 companions that are co-moving with the central star. So they are very likely bound. So we have one B0.5 type star with a 0.30 solar mass companion. And the spurious association probability, newly calculated based on that they are co-moving, is 0.08%. That is a lot lower than what we previously had, at least 10 times. And then secondly, we have an O9.7 type star with a 0.13 solar mass companion, where the spurious association probability now is 0.9%. So because we are still relying on these spurious association probabilities, especially for the brown dwarfs, we would like to have some alternative way of confirming them, because brown dwarfs are very faint, and that means that also the background contamination at these faint magnitudes is a lot higher than at the slightly brighter magnitudes. So what we try to do is make some different combinations of color-color plots and see if in this way we can separate brown dwarfs from stars with other spectral types. So I did this here, and the different circles that you can see, or the dots, are again from the Besançon the Besançon model of the galaxy. So these are stars with other spectral types. And then the stars that you can see, these are the expected colors of young brown dwarfs. So they are still pre-main sequence forming brown dwarfs from the BT settle models. And then you can see in this JHL diagram, we can actually separate them quite well. Now, measuring J and H can be done with sphere. We submitted a proposal for that, and it was accepted, so hopefully we will get the data this year. L-band you cannot get from sphere, and at the moment there's no instrument on the ground that can do it at the contrast that we need. It is possible with James Webb, but yeah, it's proven to be quite hard to get the data, but maybe once we have the sphere data, it will be a bit more convincing. At least if by that time we still think that it has the right colors to be a brown dwarf. Okay, then finally we can discuss also some different potential formation mechanisms for these low mass companions. So as I discussed in the beginning, core or filament fragmentation, there it is very unlikely that you would get one very massive star and one very low mass companion. So we don't really see this as a likely pathway to have formed these systems. Disk fragmentation, however, might be possible, although simulations predict that the fragment masses are around 1 solar mass, which would be too massive for our companions. But then again, we don't know yet what the fate is about from these fragments. And also, there's still the question whether a companion or a fragment that is still forming can even survive in this environment where the UV radiation is so strong. And then finally, capture. That's also a possibility. At this moment, just based on the 2 observations that we have, we cannot distinguish this from any other formation mechanism. But what you can do is that you can increase the statistics on these low mass companions, see how many of these we actually find and how many of these we can confirm. And then you can compare it with embodied simulations, as was, for example, done by Parker et al. 2022. So they did some simulations specifically for some exoplanets that were found with high contrast imaging around B-type stars. And for their region, they found then that such a capture happens about once or twice in the age of the association that they studied. But of course, such simulations could also be repeated for specifically for the ages and densities of our clusters, and taking into account the higher mass primary stars. So then, for the last part of this talk, I want to introduce you to what I am doing at the moment, which is the bias correction. So I've talked about this already a little bit. Why we need this bias correction is really, for example, if you want to compare the O-type and B-type companion fractions, where we found this weird thing where the B-type companion fraction is larger. We need to take into account that the sensitivity limits might be different. If we want to compare the results from different clusters, we need to take into account that they are at different distances, also that the sensitivity limits might be different. So it's important that we get an idea about the intrinsic multiplicity properties, not biased by our instruments, for example. So this is really a work in progress. So I'm sorry, don't be too disappointed. There's no results yet, but I rather want to show you the ingredients that we need to develop this tool. So the observational biases are linked to detection limits. So we are biased towards wider and brighter companions. We might miss some specifically closer companions because in terms of brightness we are going already quite faint. We are also biased by the orbital parameters and projection effects because the fact that your binary will move around means that sometimes it can move like in and out of the field of view. So that could also lead to incompleteness in a sense. And then, of course, we are biased by the fact that we have a lot of background contaminants and we need to separate them from true companions. So the goal of this bias correction is really to get an idea about the intrinsic multiplicity properties and the mass and separation distributions that are underlying. So what we want to do is we want to find the models, the mass ratio and separation models and the background models that best reproduce our data. So we need to have a look at the probability distribution function of companions and to that of the background sources. So that are two main ingredients. For the companions, what we need to take into account is the detection probability. And that means both the sensitivity limits and the orbital parameters and projection effects of the binaries. Now, for the background sources, that is actually a distribution that by now I think we understand quite well. So there's two main ingredients that go into that. The first one is a magnitude dependence. So this plot shows you the K-band magnitude on the x-axis and the cumulative star counts in a certain area on the y-axis for different catalogs and models. But so the y-axis is in a logarithmic scale. So actually this goes up exponentially with magnitude, the number of background sources that you expect. And then secondly, there is a separation dependence, because if you go to a larger separation and you draw like a circle, your area gets larger. So that means that you are getting more background contaminants at larger separations. So then for the companions, so I talked a bit about the fact that we need to include also the fact that orbital parameters can change and that we have these different projection effects. So what we want to do is actually translate the true separation, which will be in our model, to an angular separation, the projected angular separation, which is the one that we measure. And actually, a certain combination of orbital parameters can also have different angular separations. So here you can see a projected orbit, so a companion that is moving around a central star. And then on the right, you can see some like the different projected separations that it can have. For example, if you look at the bottom plot, it gives you a histogram of the different projected separations that occur for these specific combinations. And then you can see that there's a peak at the wider projected separations, which is what we would expect because of Kepler. Like, especially in this regime, you spend more time. But what we didn't necessarily expect is that in some cases, like this one, you can also get a peak at the front. So, and that is just because here, if you can see it, like it resembles a circle more. So you will stay closer to the star at this point. And this is important for us because it means that it's not necessarily the case that a companion will spend more time in our field of view. For example, if the semi-major axis is really at the boundary of our field of view, it might also spend a significant amount of time behind the corona graph. So if we combine these orbital parameter and projection effects with our sensitivity limits, we can build something like this. And this is a completeness map. So what I did to calculate this is that for each combination of semi-major axis and companion mass, I drew a number of parameters for eccentricity, inclination, argument of periastron, and I calculated what would be the angular separation for all of these different combinations. And then I every time checked if at that angular separation, the companion would be detectable. So would be above or below our contrast curve. If it's above, we give it a probability of 1. If it's below, we give it a probability of 0. So, and then you can really see the effect of sources sometimes like moving in and out of our field of view, or sometimes with certain projection effects being detectable or not detectable for the same semi-major axis and mass combination. And also even if you would directly translate our angular separation of the field of view, 6 arc seconds, to AU, this will be around 9,000 AU, so you can see that we are also getting some companions from the wider separations that are sometimes moving inside our field of view. Okay, so then it's time for summary and conclusions. So what we found is some that our observations show some hints already for a migration mechanism, and we also found that a very high density, cluster density, likely leads to a lower wide binary fraction, although we would have to do some bias correction to be sure about these effects. We also detected 2 low mass companions around an O and early B-type stars, and these are some of the lowest mass companions that have ever been detected around such massive stars. But the formation channel of these companions is still unclear. So what we would need to do to get a better idea on the formation channel is, on the observational side, we would need to increase the statistics of such low mass companions, while on the theory side, it would be very nice to have formation models that actually predict observable quantities, so that really predict what we would see like in terms of mass and separation. And then for future work, we have some more data by now, which are exciting for the future. So for example, the higher B-type binary fraction in Scorpius OB1, we have by now some additional sphere data of also a lot more B-type stars in Scorpius OB1, but they haven't been analyzed, so this could possibly also solve that problem. We have a follow-up data set of sphere data in the Carina region, so that we can also test for common proper motion of sources in the Carina region. The follow-up proposal for our brown dwarf candidate companions has been accepted, so hopefully we will get the data and we can check if they are truly bound or not. And then finally, this bias correction part will be very important, and hopefully we will get some nice results out of that, because it will really help us gain an understanding about the underlying mass and separation distributions and the intrinsic multiplicity properties, which are really crucial to be able to compare them with models. Thank you.
Thank you very much, Tinne, for a very interesting and clear talk. Are there any questions? Yeah.
Thanks, Tinne, for the very nice talk. I have 2 questions. One is about your work and one is about Emma's, actually.
Mm-hmm.
So with your work, it's super cool to see that you did include the proper motion information in your spurious detection probability thing. I was just curious, firstly, if you're only working with actual verified cluster members, right? So the cluster membership is already confirmed, kind of all your background, foreground stars?
Like of really the target stars, the samples that we got in the beginning, so we did a distance check on those, so not really, I don't think we really included the proper motion, but I think most of them share very similar proper motion, and that actually caused us to already drop one star, because one of them was not at the distance that we would expect for Scorpius OB1. Okay. So in that sense, we did kind of a membership test, I guess.
Yeah, because that would be the first thing that I was thinking of. The second question about Emma's work is on your slide 6. Yeah. Cool. You show. Yeah.
Yeah, you can ask your question already if you want. No, I'm regretting my decision to put in so many animations.
No, it was great.
Okay.
Okay. Yes. Yeah. Here, I mean, you discussed already about the multiplicity fraction increasing over the evolutionary sequence. But I was just curious: isn't there a detection limit issue as well? Because for embedded systems, you would also have. It would be just more difficult to detect systems. And then this information is also a bit contradictory, right, to the fragments thing that you mentioned, because you mentioned that the fragments can merge, they can disappear depending on the separation, etc. Yeah. But here we see differently, right?
Yeah. So you're completely right. I think the detection limits really need to be taken into account to really be able to compare this. Because, for example, so the different colors in this plot also represent different separation ranges. And you can also see, like, Emma's work is at about 60%, but then there's this other work from Pomohachi 2019, which actually they probed about the same separation range, but they find a much lower multiplicity fraction. So it might be also because of differences in the sensitivity limits that certainly would have to be taken into account to make a fair comparison. Yeah.
All right. Thank you.
Okay, I'm going to come around because there's more questions over there. Who had a question? I can't remember.
Hey, Tinne. Super nice presentation. So I had a question again about the multiplicity. So you have shown, like, in the O stars and the B stars, there's quite a bit of difference in the multiplicity. I was wondering because, I think this was like the scorpion. And then. So I was wondering, are there plans for future where you look in the more earlier clusters, this sort of, if there is, in the earlier clusters, if there is difference in multiplicity in O-type stars and B-type stars? Because I was wondering if this is, again, you mentioned about this strong UV flux, is if they maybe start out at the same amount of fragments, but over time, these O stars, they lose because of this strong flux. Yeah,
that's indeed very well possible. So, like, at the moment, for the sample in the Carina region and the sample in M17, it's all mostly O-type stars, so there's not a lot of B-type stars in there. And we don't have any proposals really planned to investigate the multiplicity properties of B-type stars there at the moment. But I think indeed it could be very interesting to also, like, also see what the effect is there. I know that there, for example, for Trumpler 14, which is a very dense region with a lot of massive stars, there are some observations planned to also test what the effect is of this UV radiation on stars that are forming nearby. So not necessarily only companions, but also stars in the direct environment, because it can also affect, like, the disks there and their final mass, for example. Yep.
Hey, I will also say very nice presentation.
Thanks.
It's really clear. I have a question about the formation mechanisms, because you're saying that, you know, based on the separation, you might be able to probe what the formation mechanism was. But some of these are overlapping, I believe. Is there maybe a way to distinguish between them based on composition, or?
Yeah, so you are completely right that indeed they might be overlapping, and you might have these migration effects where they can also move inwards. It might affect the core fragmentation formed mechanism, but maybe it also affects the stars formed through disk fragmentation. So it will be very hard to distinguish them based on separation alone, I think. What we can take into account is also the mass distribution of these companions at different separations. So if we have enough multiplicity statistics to do that, and we can perform bias correction on that and then find what would be the underlying mass and separation distributions, I think by combining the two, we could learn a lot more, especially if we also have some predictions from theory, really from maybe combining also these different formation mechanisms and see which kind of distributions you expect to come out of that, that we can actually observe.
Okay, cool. Thank you.
Okay, yeah, right.
Thanks, Tinne. It was a really nice talk. Actually, on this slide as well, you were saying it's strange that the multiplicity fraction, we assume it goes up with stellar mass, so it's weird that the O-type multiplicity is lower here. But that statement from Offner and Mona Stefano and others is based on sort of your fully formed clusters and not evolved, but proper main sequence stars, and this is a younger cluster. Could this maybe be telling us that the O-type binaries are forming later? Is this maybe sampling early on in the formation?
I'm not sure, because at this point in Scorpius OB1, I think the stars are already fully formed. So they are main sequence O-type stars. They could potentially be some more stars that are forming through capture, but that is seen as a bit more unlikely, maybe. I mean, I wouldn't expect such a big difference for that, but I lost my train of thought. No. Yeah, I remember. So what this could be telling us, I think, if this is a real effect, then it would be very interesting to look at the low mass, like at the mass distribution of these two types of stars, like if we can see a difference in the mass distribution for the B-type and O-type stars, for example, because this could mean that B-type stars just have more low mass companions than O-type stars. And actually, this is not that strange to think of, because O-type stars emit very, very strong UV radiation. So this could just mean that in this very strong UV environment, the low mass companions just cannot survive. That's just a thought. There's a lot of steps we have to take in between to get to that conclusion. But that's a possibility, I think.
Sure. And then on page 29, slide 29, whatever it was, you had this difference. You were looking at the background contamination. You said that the IRDIS background sources have these really big error bars, but the IRDIS, I think you said this is like a confirmed companion, has much smaller error bars. Why are the errors so much larger on the background sources? And could you use that to as a way to sort of mask out some of the noise?
So you mean, why are the error bars on the IRDIS background sources so much larger than the ones that we have over there?
Yeah, you have an IRDIS source over there. It's the same telescope, right?
Yeah, the one at the top?
The
the red
CC1
ones.
there,
Yeah. Okay, yes. So the reason for this is that, so this candidate companion 1, that is in the IvS field of view, so it's really close to the central star. But for example, because of the plate scale, there's the pixel scale of the detector. If you get to wider separations, you will keep propagating the pixel scale error, because it's measured relative to the centering of the central star. So if you have already a small error on your pixel scale, the more pixels you are away, the larger that error will get. So I think that is definitely one of the reasons why these error bars for the IRDIS sources are so large.
So you could have a background source that was physically nearby the star and it would have smaller error bars?
Yes.
Okay.
Yes.
Thank you.
Yes.
Hi. On the background stars, again, I have a question, because you study the proper motion, so indeed it takes some time to see if they are behaving differently, but do you have data of the radial velocities of these stars?
No, we don't have it, and I think it would also be difficult to get it, well, at least at this moment, with coronagraphy, because, for example, the spectrum that we can get, it's very, very low resolution, so to try to find radial velocities from that, I think it's impossible at the moment. But yeah, it could be nice, indeed, if you could really see that it is orbiting around the central star. But for example, if we would want to follow the orbital motion, because that's also something that is done a lot for exoplanets, but because we are looking at stars further away, the resolution is also much worse. We are looking at stars that are at very large separations from their central star, so we're really probing orbital periods of thousands of years. So it's, that would be, I think, very difficult. But maybe radial velocity in the future somewhere could be a solution.
Okay.
Hi, Tinne. Again, great talk. I was wondering about the brown dwarf companions. You're trying to, single them out or try to identify them relative to other stars from the photometry, so your JHL magnitude. I was wondering, are you also considering trying to disentangle them spectrally? So really trying to get a spectrum, for example, with an IvS?
Yeah. So definitely we are trying to, we already have spectra for them, because that's how we kind of characterize their mass and characterize that they should be in the brown dwarf mass regime. The problem is that at the moment, the the quality of those spectra is really bad. So especially at the J and H wavelengths, we barely detect it. We don't even see it in some of the channels. So that's also part of the follow-up sphere proposal, so to try to get a better spectrum. The problem is that just from the spectrum alone, so you have to put a range of ages in which you will fit the spectrum, because there's a degeneracy between mass and age. So your companion can be older and have a lower mass, or it can be young and have a higher. Is it the opposite? I don't. Yeah. So well, in any case, young brown dwarfs are brighter than older brown dwarfs. So. So I don't know if from the spectrum alone we can really see. I mean, of course, it's also a spectrum. I mean, the J and H and L bands. So I think this is really the way to go to try to separate them.
Are there any further questions?
Okay, I will also want to repeat. Great talk.
Thank you.
This might be a little bit of a naive question because I don't do observations, but can you comment on, have you looked at the separation between the stars, and can you have you found any relation, anything?
Like the separation between the different stars in our sample?
Yes, yes. So there's the separation, so you have found like the binary diffraction, but the, have you found anything about the separation, any relation or any?
Like the separation of the companions with respect to the central star?
Yes,
or
yes,
okay, okay.
yes.
So, yeah, I think that is something that will really come out of the bias correction work. So, because then we hopefully will be able to really get the underlying separation distribution just of the companions, because right now we are also contaminated by the background sources. So it's really difficult in that sense to say a lot about the separation, because in any case we are detecting a lot more sources at wider separation, but that's just because the background at wider separations, well, you have the larger area, so you will have a lot more background sources. But really to separate the companion separation distribution from the background, I think the bias correction will help us there.
Okay, so we should wait for your
okay. For the defense.
Thank you.
One last question? Yeah. Okay.
Thanks, Tinne. That was a wonderful talk.
Thank you.
So my question on the O and B and the multiplicity faction, do you have plans to accounting for the different luminosities of the O and B stars inside your bias correction? Because naively, I might expect that nonlinear scaling of luminosity to punish the O stars quite heavily, and particularly for the low mass companions. So I wonder, or maybe that's already factored in.
No, so I think definitely the bias correction will take into account, that's a hope, will take into account the sensitivity limits. So to make also a more fair comparison, if, for example, around the O-type stars, we can detect less low mass companions than we can around the B-type stars. So that should be taken into account. On the other hand, like something that could also be interesting to do, for example, is really comparing the different luminosity classes within the O and B type stars to see also really what the effect is of those. But I think the sample right now is not big enough to do that.
Fair enough. And if I'm permitted, one quick one. So it's interesting that with just 39 wavelengths, you're able to get out masses and who knows what else. I guess I'm wondering, like, from a position of normal spectroscopy and how usually people don't even attempt to get out a mass from an atmospheric model. Like, how is this possible?
It's a very fair question. And I think you should really look at the masses that we find as estimates and not as a true mass. Because we indeed sort of make a comparison, we do a least squares fit. And then to find the error bars, for example, we take into account all the models that fit to our spectrum within 3 sigma. But you're right, the resolution is really low. We also need to put a constraint on the ages. So because we have this degeneracy between mass and age. So yeah, there's a lot of uncertainties that go into there.
No worries, thanks.
Okay, one very last quick question.
Do any of your stars have oscillations?
I think some of them might. I'm not sure. Yeah, but possibly, yes.
Okay, I think we've reached the hour, so we can thank Tinne again. Thank you very much for coming, and see you next week.